So I just wanted to really quick show my little test station setup. Now, I highly recommend doing something like this. This is invaluable to, your workflow, and especially when you set up a machine. It'll be able to decipher if something on here went wrong or was it the machine's incorrect setup. So, power supply, motor drivers. Some of these motor drivers actually come with power supplies built in, which is a nice feature. So you can provide constant current to the motors. And breakout board right here. You got your motors. I got NEMA 24s. This is a 4-axis breakout board driven by parallel port, and I have a designated computer that I run Mach 3 with, and my cam software is on my laptop, so I'll be putting cam software on there so it can all be integrated. But 3D printed some flags with that 3D printer, and as you can see, was testing the type of angular rotation that I can get off and make sure it's super precise and accurate. And you want to be able to control and set up your motors in such a way that they have great acceleration as well as a good velocity, so they turn very precisely. But yeah, just wanted to show you this type of setup. If you need any kind of wiring diagrams, I can try and help, but for the most part, this was very, very helpful. Now that I have this, which I did a long time ago, it's pretty much just take these and throw it in the machine.
Alright, so this is part 2 of the video. So this is just me setting up the electronics before I put in a more permanent structure. So a couple things, just make sure you do cross one of your pulsing directions for your slave motor, so either the black and green or the blue and red. And also check your power supply. I ended up blowing a capacitor up on my breakout board just to too high of a voltage. So for now, just check functionality, heat shrink everything, keep it as neat as possible.
So all the wires are properly hooked up, but as you can see, it's a pretty big rat's nest of wires, and the machine works fine, but I'm gonna have to do something about these guys and all that gunk over there. So I went to Harbor Freight, grabbed some of this conduit, and I'm gonna basically just wire up everything I can just so I can, be a little neater and less in the way. I grabbed a wire hanger, which I'm gonna feed through with this conduit, and then it'll basically create an arc. I don't have a drag chain, nor do I plan on doing one soon. Kind of want to expedite the process and get this thing running, but to keep these wires out of the way, I spiraled around a sprinkler wire, some scrap wire I found, and then fed a coat hanger wire through the length of it. And I did the coat hanger wire for the other two conduit as well, and then kind of zip tied them all together, loosely, so it has a little play. But basically, see these the coat hanger wires, they're mounted on spindle mounts, and to the gantry plate right here, just made a hook, and keeps a constant arc as it translates, so it works really well. So yeah, that's that. And then also, I needed an electronics enclosure, so I built this guy. Took about half a day or something, but just used melamine for the top and bottom, and 2x4s that you face on the table saw, and miter cut them, and glue them and screw them, and pretty much have yourself a box. So as you can see, here's power supply, and there's one on the other end there. Just didn't have as many terminals as I needed, but also have the spindle motor driver, and then the 3-stepper motor drivers, and then the breakout board. Fixed this little block of wood right there. Notched out a little notch for the parallel port wires and USB. So here's my desktop right there. So also had a little time, but 3D printed some handles. Those are actually probably the best thing on here. But for the back end, just had some scrap hinges painted in. Notched out this little back area here so the conduit can freely move as the machine translates. I'll bundle them up a little better, but wanted to note that basically I have a couple extra fans that I'll be hooking up to this power supply here, but you need airflow going through the length, so I'm going to see if that fan is powerful enough, and really see if I even need a fan. Some of these electronics, unless they're not running for an hour, a couple hours, then they're really fine to be in just an enclosed box like this without that much airflow. But obviously it's wood, it's a fire hazard. I'm not going to be CNCing unless I'm close by or around this thing. So if you need any design ideas, this is what I did just for now. So here's Mach 3 open. Now I tuned the motor velocity acceleration curves, and this is the type of movement I've been getting on the machine. So it's real responsive and immediate. So that's going to work for me. However, I'm going to redo this wiring. Something's going to get caught in this cluster and then yank out some wires, so I can't have that. Another thing is, the motor's output torque is, sometimes so high that you are still going to be limited by the belt drive. There will be slippage if it's too fast, so, lower your acceleration. component on the curve. I did add a potentiometer so I can adjust the spindle speed. So that'll be nice. I'll actually take that off and just use the pulse width modulation on Mach 3's interface. But so next step is going to be adding limit switches and an e-stop. Stay tuned. Alright, so mounted the potentiometer for the spindle on the outside, as well as the rocker switch for the e-stop. That's all wired up and works properly. Right now I'm just doing the limit switches, so just using solid copper wire to female disconnect and crimping it down, and heat shrinking the shrink wrap over the terminal, and just trying to decide on a way to mount these right now. Looks like I might even just zip tie it, but it's going to go in series all the way around the machine and then to the breakout board and electrical housing. Alright, so I have all the limit switches put in. They all work really well, so, as you can see. Now all I did was super glue them on the back side and hold them in place, and then zip tied them afterward. So they're all put in place and they worked well up until this happened. So capacitor blew up on the breakout board. What I think happened was 2 wires were switched on the terminal block there, and it reversed the polarity going through the capacitor. So capacitors don't like that, so that's alright. I ordered a new board and it'll be here tomorrow. These things are really cheap. I think they're about 12 bucks. And once I get that put in, next step is going to be putting in homing switches for the XYZ and some soft limits. Alright, so this is going to be the real reason that the capacitor on the breakout board blew up. So this was the power supply being hooked up to the breakout board, which was 48 volts, and there's a 12 to 24 volt range for the breakout board input, so it's back here. Ultimately, too much voltage, too much current going through the 16 volt, 220 microfarad capacitor. So, obviously it blew up. So, that happens. But I want to check the other power supply and see if it's outputting the same voltage that it was designated to, and this is definitely not. It's supposed to be 24 volts. So this is the lowest setting on the potentiometer, so you use the adjustment screw on the corner there to actually change that voltage. But still, it's not, that's a okay voltage for the stepper motors. However, I just ultimately used this wall wart, universal wall wart, with a 12 volt selection on there that's hooked up correctly to the 12 to 24 volt input, and that'll be powering my limit switches and stuff. So just a reminder, check your power supply voltage so nothing gets harmed. And next step is going to be to check if that new breakout board works, and it should. I think all my wiring's correct, but pretty much, stay safe, don't blow anything up. This is test number 2 with the new breakout board. Got my safety glasses on, and I'm about to power it up. And just in case I did not do everything correctly once again and fry my new breakout board, I'll let you guys know what happened and I'll videotape it for you. So here we go. This is power on. Alright, seems to do okay. I really should get a thermometer to check if the capacitor's heating up, but see that diode in the corner there? That's the 12 to 24 volt switch signal, so it shows that you're supplying the correct voltage. Or any voltage really, but nothing seems to be going wrong. I'm going to turn on the computer and see if everything's okay. Alright, so it is cold to the touch. Everything seems to be working fine. This is the capacitor that blew up last time. So everything seems to be in order. And whew, that's a relief. Been milling and trying to test out its capabilities. So what I'm doing is actually milling in the lateral direction, just to test the capabilities of the motor and the belt drive system right here. So it is slipping, as you can see. I pretty much tightened the belt, and it got ultimately to here and slipped. So normally what you want to do is actually just make small incremental changes in the lateral direction and then mill longitudinally, because you got 1 and 2 motors, so you got a higher lateral or longitudinal output force. But for now, what I want to do is actually increase its lateral force by, let me see if I can focus, by increasing the angle on that belt to that timing pulley, so it creates higher tooth engagement. Now there's a couple ways I could do this. Is one, I'm going to take these idling wheels and lower them down, or what I'm going to do as a quick fix is go ahead and 3D print new ones with a higher diameter, and it does the same thing, increases the tooth engagement on there. What I just want to avoid right now is just re-drilling that gantry plate and taking everything off. So ultimately, if that doesn't work, I can actually go ahead and drill a new hole right here, and take one of these kind of wheels and sandwich that belt down on that pulley. So it's basically like an idling wheel, you know, compressing that belt down. So if there is any kind of slack that builds up in this belt over time through the vibration or whatever, then hopefully it'll keep it on track and, you know, keep the tooth engaged. So that's pretty much my issue now. I'm going to go ahead and see if the 3D print works. Alright, so here's the new idler. Make sure there's that inset in there for the bearing, and see how it turns out. Alright, here we go. This is the first test after the new 3D printed idler wheels were put in. The graded dimension is providing plenty of tooth engagement on that timing pulley. I basically retightened the belt, shortened the belt up actually a little bit, just because I had to tighten it a little bit better, but one of the reasons I actually found out that there was too much force being applied, so slipping the belt drive, was, again, it was slipping, or sorry, it was scraping on the linear rail, one of the nuts for the stepper mount right here. You know, all I did for now is just put brake caliper grease on, just because it was doing it lightly enough that I'd get away with it, but eventually, just like I did for that other guy, I'm going to go ahead and take off the gantry plate and basically grind down that nut, just enough that it won't even touch the rail. But for now, it's doing great, and, you know, it seems to be working just fine, and I think it'll hold up for quite a while. So for now, I'm just going to start incrementing laterally and milling longitudinally, just because I got plenty of torque on that longitudinal axis, so it's doing great.